The stars have aligned. I have almost everything needed to complete one of my longest awaited projects. The robot, the controller, and most importantly, a forklift to move it all. The last thing I need is some wheels. Big wheels. I need to move around a 3,000-pound industrial robot built for speed, which means I need a wheeled base that can both handle that much weight and also still be stable enough to not tip when the arm is moving at full speed. I of course considered making one from scratch, but the cost and complexity quickly got out of hand. Instead, I think finding some old piece of heavy machinery might be the way to go. After scrolling Facebook Marketplace for the past few months, I came across this sad thing. Basically an overgrown scissor lift, but meant for rough terrain instead of smooth concrete floors, with foam-filled tires and four-wheel drive. It's in New Jersey, 300 miles away, so I'm not going to go look at it in person, and I've been looking for a machine for long enough that I don't think I'm passing up on this one in hopes of finding another in better shape or closer by. Even if it's in terrible shape and needs a lot of work, I'll probably still make it out ahead compared to any of the other options so far. The Facebook post said it ran when parked, and we all know what that means, so I had to pull it off the trailer and start to figure out what's wrong with it.
Good. Looking good. Keep going.
The goal now is to see what works, and if it can still drive and steer. I couldn't care less about the lifting section. All I need is the lower frame and the stuff that runs the hydraulic motors at each wheel.
We were able to get it off the trailer without much hassle. The engine side is looking not horrific. The story is this supposedly sat out in a field for at least 8 years, quite possibly more. Luckily, both of these little boxes on each side of the machine had sheet metal covers over top of them, so it did protect the engine from, I guess, just being completely exposed. The engine looks like it might actually run. We're going to see about that here in a moment. Over here on the other side of the machine, we have the main hydraulic tank and all the hydraulic valves, then the electrical controls for everything, which look to be in significantly worse condition than the engine and pretty much everything else here. I'm going to just jump out all of this stuff so we can just get fuel and spark and see if it's going to run or not. Then if it actually starts up, we'll see about just jumping power to some of the hydraulic valves, getting the wheels turning, and see if the steer valves and everything work properly or not. Before we try to start this up, we'll check to see if its fluids seem decent at all. It is wet down in there, but it is not full, so we'll top that off. Check the oil. Hopefully this thing isn't full of just water. I don't see any water on it, which is a good sign. It looks like it's completely full to me. Before we try sending power to this through the starter, I just want to see if this moves. Make sure we're not going to destroy anything immediately. Yeah, seems like it turns over just fine. The gas tank, unfortunately, was open, possibly the entire 8 years this thing was sitting, so I'm not going to rely on anything in there. We'll just pop that fuel line off and feed it some nice new gas instead.
Remarkably, the engine starts up and runs just fine. It's set up to run gasoline or propane, which is super convenient since I could run it inside of a warehouse just like propane forklifts. There's a bit of an issue with the starter not engaging properly, but I can get that fixed later. The biggest thing now is seeing if it'll drive. I disconnected all of the solenoid valves and engine controls from the original electrical wiring on the machine and hooked them up to manual switches on this little test board I made. I'm not going to attempt to repair any of the original wiring on this machine, especially considering it's all getting torn out anyway when I replace the controls with my own. Speaking of my own controls, I've been working on the next version of the robot controller hardware, which should fix all the issues I found while making the first version. One of the biggest changes is these new 3-channel servo drives, which can run 3 motors at once while only being slightly more expensive and larger than one of the old single drives, greatly reducing the size and cost of the entire system. Thanks to PCBWay for helping sponsor these projects. I ordered 5 of the new servo drives to start and had PCBWay assemble all of the SMD components for them so I could begin testing right away. You can upload your board files as well as the bill of materials and component placements. Then they'll order the parts and assemble everything for you. In my experience, they do a great job catching incorrect footprints or parts. It's really nice having a second set of eyes check over my boards. I of course still had a couple issues on this design as usual for first revisions, but that was no problem to fix myself. Visit PCBWay using the link below to get a discount on your first order. The new servo drives are still in development, so I won't be using them today, but hopefully pretty soon they'll be up and running the robots.
We can try starting it. Steer? Nothing. Don't see any steering.
The hydraulic drive works, but the steering doesn't, and it also sprung a leak.
Ooh. We're leaking something over there.
Looks like the fitting that one of the drive hydraulic lines connected to has rusted through. Not surprising considering there was probably wet leaves and dirt covering it for years. It isn't leaking too bad, so in the meantime, I'm going to try to get the steering working. Then I can drive it to a better spot for me to work on. I decided to check the valve itself first to make sure it wasn't stuck.
We're going to hook this up and see if we can see the spool moving around inside. Seems to work to me.
But after that, I realized the valves I was looking at didn't match the schematic I found online.
Oh, interesting. I wonder if this one needs to be on for us to get steering pressure. So this whole section here isn't shown in the schematics.
Okay.
And this controls the tilt and like basically the leveling of the basket.
Okay.
Now the schematic shows there being the steering relief valve in one of the ports that this is now attached to.
Okay. So that's probably with this thing on the back.
So I'm thinking that solenoid on the back over there that isn't shown anywhere, I'm thinking this might cut off flow to this stuff and just make it so only steering has that.
This is the hydraulic schematic from the manual I found online. Note that these valves I mentioned before that control the platform leveling are not present in this version, so I'm doing my best to fill in the gaps. Now, I am by no means a hydraulics expert, so if you are and I say something stupid, feel free to leave a comment. On the left is the main pump that's attached to the engine. It is always running and produces near constant flow. It pulls fluid up from the hydraulic tank and pressurizes the rest of the system. The main pressure relief valve opens and lets oil flow back to the tank if the pressure gets too high. In this case, around 2000 psi. What we care about for steering is this point here, where the flow gets divided between the steering and drive controls. The flow divider isn't just the T-fitting, it's a special valve that regulates the flow going to the steering controls to ensure they will always work, even if the drive or lift controls are using oil from the other line. Here is where I hit inconsistencies between the manual and my machine, because according to the manual, all I need to do is activate the steer solenoid valve to send fluid to either side of the steer cylinder to move it left or right. Yet when I do, nothing happens.
Nothing.
Since the valves that connect to the leveling cylinders are bolted on top of where the steering pressure relief and plug used to be, I think that the flow actually goes up to them first, and then needs that extra valve on the back of the block closed to divert flow into the steering circuit.
I now have that solenoid on the back of the valve block hooked up to our throttle switch, since there's no throttle solenoid over on the engine actually, it's just bypassed. Fuel on. Start it up. And flip that switch. Alright, it does something. You might need to steer then flip it. So we're steering right, flip the switch. I think that's left, but...
After I powered that extra valve, the steering finally worked. I found the steer valve needs to be actuated before that additional valve, otherwise the flow has nowhere to go and it opens up the pressure relief. With it finally driving and steering, I got it positioned so the forklift could take off the platform and lift sections. This is why I said the forklift was the most important part. This project would have been essentially impossible without it. I didn't have a forklift around here until recently, and out of all the different machines I've bought to help me make different parts or do different things, the forklift is pretty high up on the list of opening the door to new projects, especially when the response to how much does it weigh is in tons instead of pounds for more and more of my projects. What used to take a whole weekend and a bunch of steel pipes and friends with crowbars can now be done in 30 seconds while sitting down. Absolutely life-changing.
So we need to cut those bolts that are holding the basket onto the telescoping part. There's 8 total, 4 on each one of those little pads. And then we should be able to lift this whole thing off.
Hear it moving.
There we go. Is that both of them or just one? Oh, we got it. Awesome. That's so close. Pick it up again. That's so close to coming off. It's ridiculous.
With the top platform removed, I was able to reach the leaking hydraulic line from earlier, and I managed to twist it right off.
Oh. Well, yep. That would be rusted through.
I spun that off and it just completely snapped off on the other side. Not connected at all.
The replacement hose is ordered, but I was too impatient and stole the hydraulic line from the main lift cylinder to get it up and running again. Now the fun part begins. Before I switch all of the controls over to the final industrial stuff that will also run the robot, I'm going to make this thing remote control. That way in the meantime I can move it around easily and test everything out. Controlling the solenoid valves is super straightforward, just a bunch of relays. The proportional control valve is a bit more tricky. It's how the variable speed drive on the machine works. The valve gradually closes further the more voltage is applied, directing more flow to the motors that drive the wheels. I've been switching it fully on or off for testing so far, but true variable control would be better. For that, I'm using this motor controller board to send a variable PWM signal to the valve. Everything is run by this microcontroller, so I can program which valves need to be on for each action. Luckily, there isn't anything too complex going on with the controls. I linked the left and right stick movement to trigger the solenoid valves for steer direction and steer enable, and the forward and backward stick movement controls the forward and reverse solenoids, with how far I push the stick controlling the proportional valve to give variable speed. Then finally, the high and low range is controlled by this switch on the top, which activates the high and low valves in the drive hydraulics. With it finally all up and running, I started to take it for a test drive, but that was cut short.
I appear to have not unlocked the tilt cylinder. Whoops. I think we might have blown another hydraulic line.
I can't say I'm surprised I blew another line. I'll need to replace every hydraulic hose in this machine eventually since they're so old. Luckily, the replacement line I ordered arrived and fixed the original leak. Then I could use the longer line I stole from the lift cylinder to fix this new line that just blew. I also realized the floating axle wasn't unlocking, which was why that back tire lifted up off the ground. The front axle is attached to the frame through a pivot, letting it follow uneven terrain. However, there's also a cylinder attached that keeps the front axle locked in place, letting the frame remain rigid when the platform is extended, keeping the entire thing more stable. Looking back at the hydraulic schematic, there's another valve that controls pressure to 2 check valves on the cylinder I just mentioned. When pressure is applied, those check valves open, allowing flow in and out of both sides of the cylinder. With that valve off, the machine is rigid and has a tougher time climbing over bumps since it needs to lift the entire frame over. With the valve powered, the axle can tilt, keeping all 4 wheels on the ground, making it much easier to climb over obstacles. You can also see one of the nice advantages of a hydraulic drive system compared to a normal direct drive transmission. It's easy to slowly inch over a bump. It doesn't roll off once I get to the top. Not saying you can't do this with a normal transmission vehicle, but it requires quite a bit more control and feedback than just a single hydraulic valve. Now at last, I can get back to the test drive. It's a bit slow. I mean, I wasn't expecting it to be very fast. It's meant to carry people around 26 feet in the air after all. But even in high range, it only goes a couple miles per hour, and in low range, half that. The speed is determined by the hydraulic oil flow through the motors. I looked up the hydraulic motors that drive the tires, and to my best estimate, it should be able to go at least 3 times faster than it currently does, around 8 or 9 miles per hour, if I can get the motors enough flow, that is. If we look at the hydraulic schematic for the drive motors, it's pretty complex. The remaining flow from the steering flow divider goes to the drive circuit, either through the proportional valve if it's open and back to the tank, or if the valve is closed, through the drive motors. The machine switches between high and low range not by switching gearing, but by changing hydraulic flow. In low range, the flow goes through the direction valve into the shuttle valve, which sends some flow to release the parking brakes in the 2 rear drive motors, then into this counterbalance valve, which I'll explain in a moment. For now, just imagine it doesn't exist. Then it splits into 2 motors, then through the other 2 motors, and finally back through a flow combiner to ensure both sets of motors have equal flow. This ensures that all 4 wheels will stay spinning even if one of the groups loses traction. If the flow combiner was just a T, when one set of tires lost traction, all flow would go through that set and the machine would get stuck. In high range, the flow goes through all 4 motors in series, resulting in twice the flow at each motor, but only half the pressure. All 4 motors plumbed in series effectively means that they are locked together, which causes some issues when turning since the tires must skid slightly to allow the inner wheels to spin slower than the outer ones.
Yeah, you can see the back wheel skidding when we're turning.
In low range, the skidding isn't as significant since the flow combiner isn't perfect and allows enough variation in flow for the different speeds. The counterbalance valves I mentioned earlier are crucial to keep the machine from rolling down hills. They only open when the pressure on the opposite line is high enough. Hydraulics can only push. Under suction, the limit is determined by atmospheric pressure around only 15 psi, while in my case, the pressure side of the drive motors is around 1500 psi. So if we were only to control the flow into the motors, and an external force is already pushing them in the same direction, the motors will pull more flow than the pump can supply, and eventually pull into a vacuum. At that point, even if the input valve is shut, there is only 15 psi opposing the motor rotating, which is basically nothing. The counterbalance valve goes on the return from the motor and closes if the pressure on the input is too low. This ensures that if the motor starts to exceed the flow of the main pump, the output is restricted to keep the motor from running away. There are 2 of these counterbalance valves, one for forward and one for backward. The motors also have a couple extra pressure reliefs between them for protection in case the machine is being towed or turning sharply and the flow between the front and rear motors varies too much. I want to get an idea of how well it'll handle driving in grass and up some steep hills, so I drove it up some of the steepest portions of our yard. In high gear, it hit the hydraulic pressure limit and started bypassing. In low gear, it was able to make it all the way up with no issues with tire traction at all. I even tried driving up this bank which was around 45 degrees and it still had no problem. Currently the main limit is with the hydraulics, not with the tire traction. I also tried this section which had some more uneven bumps and I think some bricks or wood blocks I ended up driving over. Once again, no issues in low gear. I continued driving around, it was performing great and didn't have any issues getting anywhere. I've been driving it for around 30 minutes already, so I decided to take it home before it ran out of gas.
I suspected something would happen when we're in the middle of the woods, farthest away from all my tools.
I first thought it ran out of fuel or the fuel line sucked some air in, so I let the fuel pump run for a bit and made sure we had fuel to the carburetor.
Yeah, that's plenty of fuel.
But even with plenty of fuel, it still wouldn't start. After walking back and getting some tools,
All necessary tools have been acquired.
I loosened the bleed screw on the carburetor and it had plenty of fuel.
Down there. Ew. There was an ant in there or something. Unfortunate.
I tried starting it again, and this time I was able to get it running and drive it back home. However, I don't think that bleeding some fuel actually had anything to do with it, since it stopped again later that day and I tried doing the same thing again to no avail. I think it's an issue with overheating, or some temperature related thing, since after it sits for a while it starts right back up. It doesn't show up until the machine runs for quite a while, so I'm just going to kick that issue down the road and handle the more important stuff first. Before calling it a night, I tried pushing up against the tree. I did this near the garage, so my tools wouldn't be far in case I blew another hydraulic line. In high gear, it just bypassed the pressure relief again. In low gear, it was able to just barely get the front two tires to spin. Although I'm not sure why I couldn't get the rear ones to spin, since they're plumbed in series with the front tires. My guess is that the relief valve between the front and rear motors, or the rear motors themselves, are just bypassing a little bit, which is reducing the pressure just enough for them to not spin. Either way, all four tires aren't spinning, which by my standards is totally unacceptable. I usually try to size drive motors so they always provide more than enough torque to skid the tires at full load, but it doesn't look like the people that designed this lift had the same thought. I'll see what I can do to help improve that once I get there. The entire machine is going to be overhauled by the end of this project anyway. Aside from general repairs like fixing leaking cylinder seals, capping unused hydraulic lines, or replacing some bushings, I haven't decided yet how much of the original machine and hydraulics I'm going to keep. At the very least, all of the hoses need to be replaced, which isn't too bad. The engine and hydraulics need to be moved up to the back portion, so the robot has room to sit on the main frame towards the front tires, and as close to the ground as possible to keep the center of gravity low. I don't want to have this thing tip over if the robot is swinging around fast. The robot is all electric and will have a bank of batteries to handle the high power peaks during hard acceleration, at around 20 kilowatts worst case. But it'll still need a few kilowatt generator attached to the engine to provide long-term power. The batteries and controls for the robot are going to go along the sides where the engine and hydraulic boxes are now, since they won't be tall enough for the robot to hit into. I'm very tempted to throw in a bigger engine and hydraulics so I can get full speed and torque out of all the wheels at once. But hydraulics aren't cheap, so I might just design the new enclosure to fit bigger stuff and make do with the existing hydraulics and engine for now. Let me know what you think in the comments. Once there's a robot on it, I'll have a better idea how much torque it'll actually need. Something tells me even if I max out all four motors, there's no way it will spin the tires once fully loaded. But still, certainly good enough for version 1. But before that, I want to get this entire thing properly drawn up in CAD, since I'll be moving so many parts around and need to check for clearance between everything. Having a full 3D model will speed that up a ton. I used Autodesk Inventor for the past 6 years, but have also been hearing many good things about Onshape. Coincidentally, they reached out about sponsoring a video shortly before this project, and my Inventor license had just expired, so no better time to try it out than now. After only a day or two of messing around, I started getting the hang of it, much faster than I expected. The general workflow wasn't hard to switch to at all. Onshape is completely cloud and browser based, which makes it super convenient when working in a shop or in the field if you need to view parts and drawings away from an office. I already love this feature since my designs are all available regardless of which computer I'm at. Being cloud based also means everything is saved automatically. Onshape saves document changes and allows for infinite restore capabilities, letting you see design change history and branch or merge versions, similar to how Git works in software development. This also lets you share documents easily and even keeps them synced in real time if multiple people are working on the same design. If you're an engineer, definitely check out Onshape. You can get up to 6 months of the Pro version free through my link in the description. I'll also share this design, so as it progresses, if one of you is ambitious enough to make an attachment for the robot or frame, you can see the mounting holes and everything. I think I'll get a plate attached to the frame right here towards the front tires, which gives the robot a lot of reach forward and to the sides, and leaves space towards the back to fit the engine and hydraulics. Speaking of the robot, I'm not using either of these big ones I already have. I expect this thing to get pretty abused once all is said and done, having branches or other objects fall or get caught on it. So these plastic encoders and connectors on the robot motors aren't going to hold up for long. I had also been looking for months for another robot I could dedicate to this project, but without much success. Until a few weeks ago, I found an industrial auction from a robotics integrator only a couple hours from me. I spent more than I probably should have there, but I couldn't pass up the opportunity to stock up on robots for future projects and testing. I think this is probably one of the coolest entrance areas I've seen out of any building. Robots everywhere. I was actually already here to look around before the auction. Most of the stuff from the auction is already gone, and a lot of these nicer ones are still going to be used in production. The robot graveyard outside is still full though. I believe almost all of these are going to get auctioned off in the near future. So if you want to have a go at getting something or need some industrial integration work done, it might be worth checking out the auction or reaching out to them. I'll post a video looking at the place and all the robots I got more closely in the future. Be sure to subscribe so you don't miss that. This is the robot I got to put on the machine. It's newer, has a higher payload and reach than my other robots, and is even slightly faster. It also has a metal cover over some of the delicate parts. I also want a way to guard the cables that run up the outside of the arm, since they are pretty exposed and could easily get caught on something. The machine will be a lot closer to the end total weight once the robot is mounted to it. Then I'll be able to determine how much of the hydraulics need to be upgraded and how stable everything is. Also, if anything needs more substantial changes, like adding outriggers for more support. Critically, I need to get the robot up and running. I don't have the original controller, but if you've watched enough of my videos, you know that's not a problem. I just recently got my older R2000 working with the open source controller for yet another project, so I'm hoping this slightly newer version won't be much different and cause issues. As long as the encoders use the same protocol, or are at least backwards compatible, it should work just fine. This video is getting pretty long and I think I've covered enough so far, so I'll leave putting the robot on and stability testing for the next part. If you want to follow along with this project, you can like and subscribe. It's free, supports me, and tells YouTube to show the video to more people. I'm also now selling the light up badges I designed, which were super popular at OpenSauce. This new version has a bunch of extra features and is programmable so you can upload your own image of whatever you want to display over USB. There's also some more common things like shirts and stickers, and I'll also probably put up some one-of-one leftover boards or parts for my projects if anyone wants to get a part from one of my videos. Thanks for watching.